Perfect.
You
All right.
didn't ask me. But okay.
Welcome back, everyone. For today's pre-seminar, we have our very own Antonio Del Donno, who will be talking about Weyl groups, braid groups, and quantized enveloping algebras. Take it away.
Thanks a lot for the introduction. So, as the title suggests, today we will be talking about, in particular, Weyl groups, then braid groups, and then see somehow how can we use these structures to discuss a bit some interesting things happening inside the quantized enveloping algebra of a complex semi-simple Lie algebra. So the talk is divided in. Maybe I have to touch. Let's see. Yes. So the talk is divided in two sections. First, I will introduce what the Weyl group is in a general context of a root system. I will do the same for the braid group, and then I will talk about Lie algebras and the quantized enveloping algebras. Okay, so first of all, let's start with the very basics and recall to everybody what a root system is. So we will start by considering a finite dimensional real vector space, E. Then we will take some non-zero element inside E, and we will consider this map from E to E, taking any element inside E and assigning this thing that you see here. And this is the reflection with respect to the hyperplane that is orthogonal to the vector V. And from now on, we will make use almost all of the time of this notation. So instead of writing down all of this part here that descends from the inner product that you have on here, I will just write down this Langold-Wrangle bracket to denote the same thing. Okay, so a subset of E is called a root system if the following properties hold. So first of all, we want R to be finite. We want it to span E, and we want it to not contain the zero element. Then for any element inside R, we only want its scalar multiples to be plus and minus itself. Then given any element inside R, we want that the corresponding reflection is going to permute the element inside R. And finally, given any two elements inside R, we want that this Langold-Wrangle product that we wrote here is an integer number. So elements of this root system are called roots. Okay, let's move to the introduction of the Weyl group.
Quickly, does this factor include, is it just the norm, like the inner product with the normalized V, or does it include the two?
Yes.
It includes the two.
Yes.
Okay.
I mean, if you want. Say it again, sorry?
There's only one number in R, then by number two or by number one.
Yes, I think so. Yes. Okay, but nevertheless, those are the general axiom that you give. So, as I was saying, let's introduce the Weyl group. So, the group of invertible linear transformations generated by the reflections S alpha for the roots inside the root system is called the Weyl group of the root system, and we will denote it with this curly W of R. And we say that a subset phi of the root system is called a base if it is a vector space basis for the vector space E, and moreover, any element inside the root system can be written as this linear combination that you can see here with coefficients that are integers. And in particular, we also want that all the non-zero combination coefficients have the same sign. So the elements lying inside the base are called simple roots. And in particular, we will say that the root is positive with respect to a choice of simple roots if all of the combination coefficients are positive. And in particular, we will denote the set of positive roots with delta plus. And we will do something similar for the set of negative roots, even though they are not going to appear many times inside the presentation. Okay, so we have this proposition just to recall some of the interesting properties that the Weyl group of a root system has. So we fix a root system and we consider the corresponding Weyl group. Then we have that the Weyl group is finite if the root system is finite, which for us will be always the case. And then considering a base of a root system and a root that is simple, the corresponding reflection to the root is going to permute the set of positive roots that are not the simple root itself. Okay. And then we have this other important property telling us that whenever we consider any root inside the root system, we can always find an element G living inside this space here, which, as you may see, is just a subset of the Weyl group consisting of simple reflection. And we can always find an element G inside this set of simple reflections such that any root in the root system can be obtained by the action of an element G inside here on root alpha. Very simple. So this is basically to say that the Weyl group of a root system is generated by simple reflections, if you want. Okay, this is a very crucial fact. Okay, so some other things about the Weyl group. Again, so we consider the Weyl group of a root system, and we fix a set of simple roots phi, and then we consider as phi star the free monoid over phi, where the product is given by concatenation. Okay, so we have a sequence of simple reflections, basically, to denote every possible element that lives inside this space. And with Si, we will usually denote the reflection with respect to a simple root living inside the phi, just to have a shorthand of the same thing. Okay, so we will say that a word is a reduced word for an element W inside the Weyl group if K is minimal for this property. And we can also assign a length function on the Weyl group of a root system that is going to take any element inside W and is going to assign the size of any reduced word of your choice. Okay, so this is a map from W to N. We are sending the unit element inside the W to 0, and in particular, we are giving to W this any choice of reduced word that you like. Okay, and so here I'm stating this as a notation alert just to say that many times I'm going to refer more to this notation than to this other that we have here. Okay, so two reduced expressions are equivalent up to commutation if we have this relation here, where this relation is the transitive and reflexive closure of the relation that you can see here on the bottom. Okay, so here, notice that the only difference that we have between these two words is just the fact that in the height and height plus 1 position, we have a switch, and this is happening if Si plus 1 is equal to Si plus 1 Si. Yes, please.
So my question is
if this is a free monoid, I mean, are there relations inside this? I'm just confused by this. Because in my mind, there should be relations.
So relations are going to appear afterwards, basically. I mean, we will see that we have a different way to say the same thing. So the Weyl group indeed can be written down as a free group on some generators by quotienting via some relations that I'm going to show in the next slides.
Okay.
Okay.
Thanks.
I guess the transit plug is what switch it once.
Say it again, sorry?
I guess the transit plug is what switch it.
I don't know if I understood properly the question, sorry.
Well, it's just like the transit and reflective photo. I think the transit photo is already reflective.
Ah, okay, I see. Maybe yes. Yeah, probably. Okay.
Just for when you say is minimal for that property, what's the property? I'm confused.
So I'm just saying that you have a word assigned for some element that lives inside the Weyl group. You can write this as a product of some k elements. I'm going to say that a word is a reduced word if it's a sequence of k reflections belonging to the simple reflections of your root system. Okay, so I'm just saying that this is a product of k element, a reduced word is a sequence of k letters inside your alphabet, let's say. Okay, does it make sense?
That's why you have to start relation. There are no relations, then I don't know, in word with a
But I mean, so this is the relation basically,
Okay.
right? So this is one of the,
all right.
okay.
This deal with the free alien group, like the everybody.
So can you take even the free abelian group? I don't think it's abelian. No. You're not allowing any arbitrary switch. I want. So you see, this is basically what I'm asking, and I want it to be transitive because I'm not just interested in making a switch between two different words, but I want it to do with sequences of words, basically. Yeah, for example. And in other general cases, it's like a dihedral group, nothing more than that.
Okay. In the essence, you're referring to the section of the alphabet where you're saying one on the other, and one on the other.
Yes. Exactly. Okay, any other questions on this? Okay, so if the commutation class of an element W is a singleton, we say that W is fully commutative. This is not a thing that we're going to use quite a lot, but maybe it's useful for the next talk that we're going to listen. Okay, so let's talk about ordering and longest elements. So we are considering two elements living inside the Weyl group. We will write that U is less than W with respect to this R relation that we're going to talk about very soon, if there is a reduced word for V such that S1 Si is a reduced word for U, okay, for some index I that is smaller or equal than K and greater than 1. Okay, and this relation turns out to be a partial order on the Weyl group that is called the right weak order on W. Okay, so what it turns out is that the Weyl group equipped with this partial order is a complete lattice when the Weyl group is finite. Okay, so in our context, this is always true because we are starting with a finite root system. And so in particular, we can always take meet and joins of any two elements, where meets and joins are defined according to the equation that you can see here. So in particular, this also means that the Weyl group of a root system that is finite also unmeets a longest element. And this longest element we will be denoting with W0. This is simply the join of W. Okay, so now I'm going to tell you a little bit more about a presentation of the Weyl group in terms of generators and relation, as you are very curious about it. So we start with a root system and we fix a base of simple roots, and we write Si again for the reflection corresponding to the simple root alpha I, for I that goes from 1 to n. Then the Weyl group admits the following presentation. Okay, so it's like the group on n generators where you want that the square of each of the reflections that you have is going to give you 1, and also you want these other braid relations that I'm going to talk to you in a second. I mean, this is precisely why you are telling that these maps are indeed reflections, because of these relations that they are going to satisfy. Okay, so these braid relations are defined as follows. So we write this like commutator style bracket to between two roots, between two reflections with respect to the simple roots Si and Sj. And when we have this Mij pedix is going to just say that we have the product of some factors. And in particular, the integers only depend on the angles between the roots alpha I and alpha j. And in particular, the Weyl groups are all such that these integers Mij are all of this form that we can read here. And in particular, this also means that the Weyl group of a root system is a finite Coxeter group generated by reflections with respect to the simple roots. So if, you want the general definition of a Coxeter group is in particular a group that satisfies these particular kinds of relations. I guess that in this other case, the Mijs that you have can in principle be more general, but for us, this is what we are interested in too. Okay, so now we will introduce some auxiliary facts that can be useful for what is going to happen in the following. So first of all, we will define what the inversion set of an element inside the Weyl group is. And we will denote this with NW. This is basically the intersection between the positive roots of the root system and the action of an element W of the Weyl group on the negative roots. And in particular, this can also be understood as the set that you can read here on the right, but this for us is not very important because there is another way to talk about the inversion set of an element of the Weyl group that is the one that is going to follow now. So given any reduced expression for any element of the Weyl group, it can be proven that the inversion set can is precisely what you read here. So, for example, you start with this decomposition S1, S2, Sk. So the first element inside this inversion set is the root corresponding to the reflection with respect to the root. So if you want, it's just the root with respect to you are reflecting to. The second one is the reflection of the first applying on the second root, and so on until you are spanning everything on this other side. So in particular, if we have two elements, V and W, living inside the Weyl group that are comparable with respect to the partial order, and in particular we have that V, is less or equal than W with respect to R, then the inversion set of V is contained inside the inversion set of W, as it is very evident from the definition itself and the definition of partial order. Okay, then we have this interesting theorem from Matsumoto that is telling us that basically reduced expressions for an element of the Weyl group are unique up to braid moves. So in particular, this is a result that is going to be true even for more general Coxeter groups. So we start with a Coxeter group W, and we have that any two reduced expression for an element W inside W can be obtained one to the other just by applying repeatedly the braid relation of the group itself. Okay, any questions so far? Yeah, let's go. Yeah. So you want that SISJ MIJ is equal to this other guy? Yeah. So, I mean, I will show you some examples afterwards, but basically, so think, for example, to A3, maybe A2, which is even easier. You just have two simple roots. S1, S2, S1 is equal to, yeah, exactly. Yeah, and I mean, that's why I was telling you about the example of the A series, but for example, you can think of this even in B, C, right? And it's going to be different if you're considering the special roots in these root systems, right? So for example, if you take B, you have a two special nodes, let's say, and you have two edges between them, and then the braid relation is going to change. Okay, that's it, basically. Yeah, but it's just a generalization of that fact. Yeah. Okay, so I'm realizing that I have to go faster, so 12 minutes. Okay, so it should be enough, So yeah, I mean, it's a little bit awkward, to be honest, but so you have these reflections that are with respect to the simple roots, right? So S1 is the reflection with respect to the simple root alpha 1 and so on. So alpha S1 is just a way to see that this is alpha 1, basically. This is why I was joking about it before, right? So it's the reflection, it's the root corresponding to the reflection corresponding to the root. Yeah. No, but you can think of this just as alpha 1. Yeah, but okay. So now we consider a reduced expression for the longest element of W. Then the associated set of inversion consists of all the positive roots. So let's go maybe back to this equation that you have here. It's not very hard to convince yourself that this is going to be the case, right? Okay, so it's the set of all positive roots, and in particular, this means that the length of the longest element of the Weyl group is equal to the number of elements that are contained inside the set of positive roots. Now, we consider an element beta k, an element like this that you can see here. So we are simply applying simple reflection on a simple root. And this is going to give us a total ordering on the roots that are obtained by reflection with respect to the Weyl group. And this is in particular a convex order on delta plus. So different reduced expressions of W0 are going to produce different convex orders, as we are going to discover in a while, but all of these are related indeed by braid moves. Okay, so now I'm going to take a sip of tea and then also talk about the Weyl group. Sorry, the braid group. So the definition of the braid group is like very similar to the one of the Weyl group, but it's also different from a particular aspect. So we start with a root system. In particular, we fix a base of simple roots. The braid group associated to R is the group B of R. curly B of R, generated by elements B1, BL subjected to these relations that you can see here. And here in particular with this notation, I'm really referring to reflections with respect to these simple roots that you have here. Okay, so we have the same braid relations as before, but in particular in this case, we are not asking that BI squared is going to be 1 for each of the simple reflections. In particular, this is what I'm saying here. We are relaxing this constraint. And so this is not a Coxeter group, for example. And contrarily to the Weyl group of a root system, the braid group is infinite in general. Maybe always infinite. I don't know this. Is it always infinite? Okay. Okay. Now, if we consider the normal subgroup, yeah, no, indeed, this is why I was thinking about it. You can go as far as you want without. Okay, so now we consider the normal subgroup of B of R generated by elements BI squared, and in particular, we have this isomorphism that you can read here into the Weyl group. This is curly W, sorry. So we are assigning to an element BI, so a braid element with respect to the simple root alpha I, the corresponding simple reflection with respect to alpha I inside the Weyl group. We have the following proposition. So considering a reduced decomposition of the longest element of the Weyl group, the element that you can map inside into the braid group depends only on W and not in particular from the choice of the reduced decomposition that you choose for W itself. Okay, so now let's move to Lie algebras and quantized envelopes. Why I'm interested in Lie algebras? Because the algebras provide excellent examples of root systems, in particular complex semi-simple Lie algebras to be precise. So we start with a complex semi-simple Lie algebra and we take a choice of a Cartan subalgebra. The joint action of the Cartan subalgebra gives us the root space decomposition. And in particular, phi is a subset of the dual of the Cartan subalgebra, and this is our set of roots. So we consider the real span of the set of roots, and we have that the killing form on G is going to induce an inner product on E, and one can show that this set phi indeed satisfies the axioms of a root system. So these are the reflections, again, as according to the notation that I was introducing before, and they generate precisely the Weyl group of the root system. Okay, so the Weyl group in particular acts on the set of roots by symmetries and is going to give us many important and interesting informations about the representation theory of the Lie algebra G. Okay, so here we have some Dinkin diagrams. Why I put some Dinkin diagrams? Because it's always beautiful to have a slide with Dinkin diagrams. But in particular, because I'm interested in some particular examples, so I will take as examples, for example, A3 and D4, just to show you a little bit how the action of the Weyl group on the corresponding set of roots works. So let's start with A3. So the Weyl group of A3 is consisting of three generators, S1, S2, and S3, that are corresponding to the roots 1, 2, and 3. Okay, these are the relations that you can see here. So again, we have the classical braid relations that you can expect to have in general. And also we have a relation that is just a commutation relation between the two nodes that are not linked by any edge. We also have another example, which is D4. So in particular, this is generated by 4 simple reflections, and we have the classical squared relation for each of the simple reflections with respect to the simple roots, and we have the braid relations for any 2 nodes that are connected by an edge. So actually, I could have put something more about B and C just to show you how it goes, but really the only thing that is changing is that the braid relations that you are getting are a little bit more involved. Nothing fancy going on here. Okay, so now consider the set of positive roots of A3. You can trust me that it's the guy that you can see here. And we can consider a decomposition, a reduced decomposition of the longest element of the Weyl group, in particular the one that you can read here. And again, we can consider the inversion set with respect to this reduced decomposition. And according to what we said before, is precisely the set that you can read here. Okay, so As expected, we have that the inversion set is going to give us all of the positive roots of the root system. And in particular, we also have that the reduced expression of W0 is going to induce this convex order that we have written downstairs. And as I was saying before, if you start with a reduced decomposition that is different from the one that you had before, you're going to get again the same positive roots, of course, but the convex order that you have on the positive roots is going to change. Okay. Let's move on to talk a bit about the quantized enveloping algebra of a complex semi-simple Lie algebra. And in this case, we will see that the role of the braid group on the other end is going to be fundamental. So we start again with a complex semi-simple Lie algebra of rank L, and we fix some simple roots inside this set phi. Then we fix these integers qi. So you're just taking any complex number such that this does not square to 1. And in particular, Aij here is going to denote the Cartan matrix of G. Then we define the Drinfeld G in quantized enveloping algebra as, all of you know, the free algebra on 4 real generators satisfying these relations and also the quantum cell relations that I'm not writing explicitly. We have a theorem telling us that UQG is a Hopf algebra, and in particular, the structure is given on the generator as I'm writing down here. So if you have some questions. QI2? Ah, you mean this here? Yeah.
Yeah. Yeah. But for you, it's still okay. Okay, my mind Q I the end is also because we don't want. Exactly.
We can do it afterwards.
Yeah. Okay.
Okay. So this is the Hopf algebra structure that you have on the quantized enveloping algebra of G. Not very relevant for us, but okay, it's good to have it here. So an important, very central. Yeah. I was saying this before. Yes. No, I was saying that these are the relations that you use to define the enveloping algebra, and there are also the set relations that for some reason nobody cares to write on some slides. Maybe I see why. I mean, they are not very illuminating if you see them for the first time, but okay. So why are we interested in the enveloping algebra? Because we have an action of the braid group on the algebra of endomorphisms of the enveloping algebra, even though this is more of a philosophical question, right? Are we interested in the developing algebra because of this, or are we interested in the braid group because it acts? Okay, but so we have this action of the braid group on UQG, and explicitly, this is the action, okay? So you can take a look at it for a while if you want. Otherwise, I'm going to tell you that we are really interested for what is going to follow on this guy here and this other guy here. And in particular, I'm going to show you how this look like in a very simple context. And in particular, if the angle between different simple roots is fixed, and this is what happens, for example, in the ADE series simple Lie algebras, the action on the E generators of the enveloping algebra, and you can have something very similar also for the Fs, is going to simplify quite a lot in this form that you can read here. So it's basically a q to the -1 commutator of the two generators that are involved in the action. Okay, so we consider the Weyl group of G, and we consider the longest element of the Weyl group. We take a choice of reduced decomposition, and we consider the following expressions. Those are called the quantum root vectors of UQG, or the Lustig root vectors. And you can see that this is going to be very similar to what we were saying before about the inversion set, right? So we are starting with a root and we are considering reflections. Here we are starting with a root vector and we are considering something that is very similar to a reflection, even though it's not precisely the same thing. Okay, so spoiler, quantum root vectors provide a bridge between the combinatorics of root systems and the non-commutative differential geometry, as we are going to see in a while. But to catch up everything, let's maybe make some examples. We consider, again, the linking diagram A3 corresponding to the quantized developing algebra of SL4. So we have many, but in particular, I'm considering two reduced decompositions of the longest element of the Weyl group, this guy here and this other guy here. And I'm considering the action of the braid group corresponding to this reduced decomposition. So those are the root vectors that I'm getting, and they are precisely corresponding to the positive roots that you see here on the left. Now I'm doing the same thing. So I'm starting with this other reduced decomposition, and I'm considering the corresponding action of the braid group on the enveloping algebra, and those are the root vectors that I'm obtaining. So those two guys are highlighted because they are corresponding to the same positive roots, but they have a different nesting structure. Okay, and this is a phenomenon that is very much well known in this setting. Reduced decompositions of the longest element of the Weyl group when corresponding to the braid group action on the enveloping algebra are going to give you different nested structures for your root vectors in general. Okay, and this is precisely the bottom line that I wrote down here. And maybe let's do another very quick example. So we consider now the linking diagram D4. This is just to let you see that this procedure can become quite involved. For example, if you start with this reduced decomposition of W0 for D4, you have already a set of positive roots that it's much longer than the one that we had before. But in particular, you see here that the nesting structure of this Q to the -1 commutator is going to change quite a bit. So this is just one of the reduced decomposition, but you can see that it's not very evident a priori in how to organize this nesting in structures just by looking at the reduced decomposition of the longest element. Okay, and this is all I wanted to say, and thanks a lot. There are some references. Surely. You want it in the... Yeah, this is the most general one that you have.
So take the 8 digits, difference between this action and the usual action you get from the matrix of U2 SL2, like UQSM,
So the adjoint action, you mean? You mean the adjoint action?
No, the breakthrough.
Ah, okay.
So you have an element, so you have an.
But in that case, that's an action of the braid group of the category of representation.
Yes, but you can take the representation.
And in that case, isn't it the...
Yes, that one, yeah. Right. Yeah, that's... So it's a good, I think it's addressing the very easy relationship between this and the book.
Thanks for the question. I mean, I don't know the answer, but now maybe something. Okay. So this one?
Yeah. Can you explain again, like what is the role of this reduced weird decomposition in this table? What's happening here?
Ah, yes. So yeah, indeed.
Oh.
So, I mean, I can actually show it to you on the blackboard, maybe. So, very, very quickly. But maybe let's not think about this guy here, or yes. Yes, let's do it with this. So you start with S1, S2. Ah, thanks a lot. So you start with S1, S2, S3, S1, S2, S1, right? So now you want to start with this reduced decomposition, and you want to generate all of the root vectors that you have here. So to do it, you start with the first, that is E1. Then the second one is T1 on E2. Okay, so this is minus E1, E2, 2 to the minus 1. Then I mean, maybe I will finish just with the third one. Then you do T1, T2 on E3. And this is T1. Then you have minus E2, E3. You have 2 to the minus 1. Okay, so this is an algebra map. And this is going to give you minus T1, E2, T1, E3, with a Q to the minus 1. Okay, so now if you take a look to the linking diagram, this is 1, this is 2, and this is 3. This is going to give a non-trivial action on this guy, but this other is going to give a trivial action because they are not linked with any node. And so this is in particular now E1, E2, 2 to the minus 1, E3, 2 to the minus 1. Okay, so let's say that now, instead of starting with this reduced decomposition, you start with the other one. So you have S3, S2, S1, S3, S2, S3. And let's go maybe up just to the same point, okay? So you start with E3, then you have to do 3, 3 on E2. And this is again minus E3, E2, 2 to the minus 1. Then you do T3, E2, E1, and this is T3, E2, E1, 2 to the minus 1 with a minus. And again, for the same reason, you have that now T3 on E1 is going to give you nothing, basically. So E1 back. And this is E3, E2, Q to the minus 1, E1. Okay, so this is the difference. So you start with two different reduced decompositions. You're going to get some of the elements that are, of course, similar. So for example, the simple ones are going to be the same, right? But you're getting a different nesting in the Q commutators. And in some cases, you're going to get, I mean, even different signs, right? So you take a look at this and this, they have a different sign. This and this, they have a different sign. And these two have a different nesting structures, as I was showing here. Okay, this is the difference.
Oh, okay. Thanks.
Yeah, no, of course. But I mean, in principle, this is. And if you take a look to this other guy here, so this is going to be even more involved. In particular, if you take a look to this last guy, here you may have many different nesting structures that can appear in principle. And if you move to the B and C, you're also going to get different powers in this commutator that you have here. So it's not said that it is just a Q to the minus 1, you're going to get also Q to the minus 2, for example, if you're working with C. And this can happen in different positions. Okay. Yeah, yeah, indeed.
Any questions from the online audience quickly? If not, then let us thank Antonio again. And we'll be back in about 5 minutes for the main talk by